3 massive coronal mass ejections launched from the far side of the Sun. Each one hurled 1 billion tons of magnetized plasma toward a single tiny intruder coming from interstellar space. 3I Atlas took the hits and did nothing. It did not slow. It did not swerve. It did not flinch. The Sun reacted. Magnetic fields twisted. Solar activity spiked. The object's orbit stayed perfect and unshaken. How does something from another star shrug off the full fury of our star? Stay with this story. The data forces us to ask an unthinkable question. Is 3I Atlas only passing through, or is it probing our system? If this mystery has you on edge the way it has me, make sure to hit like and subscribe because you don't want to miss a single update as this unfolds in real time. Tell me where you're watching from, what time it is there, and what you think about this interstellar visitor. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. So, thank you for having our back. On July 1, 2025, the Atlas Survey telescope in Chile found a faint smear moving against the stars. Telescopes spot faint smudges every night. Within hours, astronomers realized this one behaved unlike any local comet or asteroid. Its path read as a hyperbola. It was not bound to our Sun. It was a visitor from somewhere else. The designation sounded like a cipher, 3I Atlas. Orbit fits sharpened over weeks. Eccentricity came back near 6.1. For context, any value above 1 means escape. 6 is absurd. The object rushed through the inner system at roughly 60 kilometers per second relative to the Sun. It will leave at nearly the same speed. Its origin likely sits in the galactic thick disk, an old stellar population. This thing might be older than our entire solar system, cutting across our neighborhood on a single pass. Observers tracked it closely. Teams calculated perihelion for late October 2025 at about 1.35 astronomical units. That distance sits just inside Mars' orbit. Close enough to heat up. Far enough to avoid vaporization. Hubble imaged the object on July 21, 2025. It showed a nucleus wrapped in a glowing coma and a tail swept back by sunlight and the solar wind. JWST spectroscopy delivered a surprise. The coma overflowed with carbon dioxide, not the water and carbon monoxide mix typical for comets from our system. That chemical fingerprint points to a different thermal history or a different birthplace. On October 3, 2025, 3EY Atlas passed near Mars. Orbiters around the red planet captured it right where the predictions placed it. No deviation. No sudden push. From Earth, the object then slipped behind the Sun into superior conjunction. Regular telescopes went blind in the glare. This is when coronagraphs matter. Instruments that block the Sun's disk reveal the faint region just outside it. Observers, both professional and amateur, sifted coronagraph frames and reported seeing a faint smudge sliding through exactly where the ephemeris predicted. Then the Sun erupted. Data and coronagraph analysis indicate 3 large CMEs on the far side of the star. They launched in rapid succession. They did not aim at Earth, so few people noticed. Their timing and direction aligned with where 3EY Atlas should have been. Picture 3 plasma cannons firing toward a tiny interstellar fragment only a few kilometers across. Each burst packed billions of tons of ionized gas, moving at hundreds to thousands of kilometers per second, threaded with tangled magnetic fields. A CME hitting a comet will compress the coma, strip gas and dust, shock the plasma. If sufficient momentum couples to the nucleus, the orbit should shift. Even a small velocity change grows into a measurable position error over days. It did not happen. The chronograph frames after the eruptions showed the object continuing along the predicted track. No measurable change in velocity. No shift in direction. The CMEs behaved as if they passed through or around the object without pushing it. That observation forces 3 options. Either our CME impact reports are wrong, or our mass and density estimates for the object are wrong, or something in the interaction prevents momentum transfer. Let us step back and confirm the basics. The discovery on July 1, 2025, led to rapid follow-up. Multiple telescopes confirmed a hyperbolic orbit. Hubble imaging constrained a nucleus radius near 1.4 kilometers, giving a diameter up to about 2.8 kilometers. Using typical cometary density assumptions gives a mass in the trillions of kilograms. JWST spectroscopy exposed a CO2-dominated coma. Polarimetry from large telescopes showed unusual dust properties. The object produced an active coma and a tail shaped by radiation pressure and the solar wind. Before conjunction, observations matched Keplerian predictions with slight non-gravitational terms from outgassing. The Mars flyby confirmed position and velocity. During conjunction, coronagraph images purportedly captured the object crossing the frames. Independent analysts reported the motion matched the ephemeris. At the same time, solar archives logged large eruptions on the far side. The claimed geometry places the eruptions roughly aligned with the object during perihelion. So what is a coronal mass ejection? A CME is not simply a flash. It is a physical eruption of magnetized plasma expelled from the corona. A CME carries billions of tons of ionized hydrogen and helium with embedded magnetic fields. Speeds vary from hundreds to over 3,000 kilometers per second. CMEs expand into space as structured clouds. When a CME hits a planetary magnetosphere, it triggers geomagnetic storms. When it intersects a cometary coma, it generates shock waves, compresses plasma tails, and can erase parts of the coma. Momentum matters. Take a CME with mass around 10 to the power of 16 grams traveling at 1,000 kilometers per second. That object carries enormous momentum. If 3EY Atlas has a nucleus mass near 6 times 10 to the power of 15 grams, even a tiny fraction of CME momentum transferred could impart tens of meters per second to the nucleus. Over days, that leads to observable orbital drift. So if those CMEs struck, why did the nucleus not move? Option 1 is miss. Space is sparse. A CME is structured and not uniformly dense. If the dense parts missed the nucleus and struck only the outer coma, the nucleus might receive negligible push. The coma can extend tens of thousands of kilometers while the nucleus spans only a few. That geometry makes missing plausible. Option 2 is mass. The nucleus might be far denser than our estimates. If density sits near rock or metal values rather than fluffy ice, mass rises and expected velocity change drops. But a dense body producing an active CO2-rich coma raises secondary questions about source and composition. Option 3 is interaction physics. Perhaps the CME energy coupled into the plasma environment without producing net impulse on the nucleus. The coma might act as an electromagnetic buffer. Induced currents and magnetic fields in the coma could redistribute forces. If the coma carries currents that generate their own fields, those fields could interact with the CME fields to redirect momentum or dissipate energy into heating rather than bulk motion. This short-circuit hypothesis sounds exotic. It proposes an electromagnetic coupling between object and star. The object perturbs local currents and field lines. Those perturbations trigger reconnect ion in stressed coronal fields. The reconnect ion releases stored magnetic energy as a CME launched from the disturbed region. The CME then travels toward the perturbation. At the same time, the object's induced currents and magnetic structure guide the energy away from transferring net momentum to the nucleus. The result is CMEs aimed at the object with little or no deflection. The idea links back to plasma physics pioneers like Hannes Alfvén, who emphasized the dominant role of electromagnetic forces in plasma behavior. Plasmas support currents and long-range interactions. Cometary interactions with the solar wind produce ion tails and bow shocks. Spacecraft have measured complex electromagnetic structures around comets. Those structures involve currents and fields. What we do not normally see is feedback strong enough to influence the solar corona. The Sun holds enormous magnetic energy compared to a small comet. But triggers exist. A metastable coronal region can sit on the edge of reconnect ion. A suitable perturbation could release stored energy without the perturbation providing the energy. In that sense, the object need only be the spark. How might the coma generate the required currents? First, composition matters. A CO2-rich coma ionizes differently from a water-rich coma. Ionization rates, collision cross-sections, and charge-to-mass ratios shift. If dust grains contain conductive materials, or if the nucleus contains metallic inclusions, conductivity increases. High-speed motion through the heliospheric magnetic field induces electromotive forces. Moving a conductor through a magnetic field generates voltage differences. At 60 km per second, those induced fields grow larger than for slower native comets. The result could be currents large enough to affect local magnetic topology. If induced currents create local magnetic pressure, they might push back against an incoming CME's field. Forces spread across the coma volume instead of acting on the tiny nucleus. Magnetic tension and pressure convert kinetic energy into heat and reconfiguration rather than imparting a net shove to the solid core. If currents form symmetric distributions, resulting Lorentz forces could cancel net translational impulse on the nucleus. All speculative but grounded in plasma physics possibilities. We need numbers. Hubble gives a diameter near 2.8 kilometers. Assuming a low bulk density around 0.5 grams per cubic centimeter, mass sits near 5.5 times 10 to the power of 15 grams. A CME with density near 10 to the power of negative 15 grams per cubic centimeter crossing the nucleus cross-section at 1000 km per second for an hour would sweep mass comparable to the nucleus mass. If even 1% of that momentum couples, we expect measurable velocity change. Avoiding that outcome requires either far less coupling or far more nucleus mass. Both demand explanation. Now compare 3EY Atlas to earlier interstellar visitors. The first, discovered in October 2017, arrived with no visible coma and showed unexplained non-gravitational acceleration. Scientists proposed exotic volatiles, extreme shape, or artificial origin. The second, found in August 2019, behaved like a conventional comet with water and carbon monoxide. It produced a familiar coma and tail. 3EY Atlas differs from both. Its inbound speed at infinity sits near 60 km per second. Others moved at lower speeds. Its nucleus appears larger. Its coma shows a CO2 dominance rather than water. Its apparent electromagnetic behavior and resistance to CME deflection add another layer of strangeness. These interstellar visitors suggest a wide diversity among objects from beyond the solar system. Each one brings a new puzzle. Perhaps the sample is too small to generalize. Perhaps interstellar objects undergo long exposures to cosmic rays and stellar encounters that sculpt properties unseen in local bodies. If so, each visitor represents new physics, new chemistry, and new structure. 3EY Atlas could be a time capsule of a different formation environment. We face a hidden data problem. The discovery and Hubble and JWST results are public. Papers and data streams exist. But claims about CMEs intersecting the object and precise tracking during conjunction sit largely outside peer-reviewed literature. Many of the coronagraph detections come from independent analysts mining mission archives. That democratization has proven powerful. Amateurs and small teams have made credible discoveries. Still, extraordinary claims need rigorous vetting. Which data sets matter most? High-cadence coronagraph imagery. Instruments optimized to monitor CMEs do not optimize for faint comet astrometry. Background subtraction, stray light handling, and instrument point spread functions present real obstacles. Precise astrometry in coronagraph frames demands careful calibration. In situ plasma measurements would be priceless. Spacecraft carry magnetometers and plasma instruments across the inner system. If any spacecraft happened to sample plasma structures influenced by the object, those records could reveal currents, field perturbations, or anomalous particle populations. Unfortunately, mission teams sometimes embargo raw data for analysis. Far-side solar observations remain incomplete. We infer far-side activity by alioseismology and by occasional stereo imaging. Confirming a source region that launched CMEs aligned with the object requires careful reconstruction. I am not suggesting a cover-up. The pace of science depends on processing, analysis, and peer review. Still, we must ask hard questions. How precise are the coronagraph astrometry claims? What are the error bars? Was the timing of the CMEs consistent with intersection at the object's position? Did later rotation of active regions into Earth view reveal unusually large or energetic spots? Those answers would help confirm or refute the CME impact story. Now widen the taxonomy. What if calling 3EY Atlas a comet misses something crucial? Interstellar objects need not fit our solar system templates. They can originate in systems with different chemistry, different temperatures, different formation processes. Consider several alternatives. First, a fragment of a disrupted exoplanet. A rocky fragment from a planetary collision or tidal disruption could be dense and metallic while retaining trapped volatiles in fractures or carbonates. Heating at perihelion would release CO2 from carbonate breakdown, producing a coma that mimics cometary activity while the core remains rock-like and massive. Second, an ancient low metallicity object from the early galaxy. Different elemental ratios could create unusual mineralogy and dust properties. The interior might preserve ancient chemistry altered by cosmic rays over eons. Third, a conductive or magnetized core. Some meteorites hold remnant magnetization. An object formed near a strongly magnetized young star could freeze a magnetic signature into metal-bearing material. A persistent field extending into the coma could change plasma interactions profoundly. Fourth, a rubble pile with layered structure. A porous outer shell loaded with volatiles over a denser core could absorb impacts and shed material while leaving the core on course. Fifth, the extreme hypothesis, artificial origin. If an engineered probe used magnetic shielding or active control, observed behavior could match. The idea remains improbable without strong evidence. Each exotic scenario makes distinct predictions. Rocky fragments give different spectral fingerprints. Magnetized cores would affect charged particle flows. Rubble piles reveal rotational and thermal signatures. Artificial constructs might show patterns inconsistent with natural processes. The route forward is data. High-resolution imaging, deep spectroscopy, polarimetry, radar returns, and radio monitoring can rule options in or out. Each observation tightens constraints. Finally, consider broader space weather links. Some suggest the active regions that launched far-side CMEs will rotate into Earth view and that timing with lunar phases might boost geomagnetic response or even influence seismicity. Those claims mix multiple uncertainties. Solar activity rotates roughly every 27 days. An active region on the far side in late October should rotate into view roughly 2 weeks later. Whether those regions produce further eruptions depends on local magnetic stress. Geomagnetic effects on Earth depend on CME direction, magnetic polarity, and coupling with Earth's magnetosphere. Linking solar eruptions to earthquakes sits outside mainstream geophysics. Correlation does not equal causation. To assess any connection, we need precise timelines, measurements of interplanetary magnetic field orientation, and rigorous statistical analysis of seismic records. What remains clear is this. 3EY Atlas challenges assumptions. It forces close inspection of coronagraph data, of solar archives, and of our models for plasma interactions. It highlights the need for coordinated observations and open data sharing. It reminds us that interstellar objects bring surprises. Each surprise offers a door to new physics and new chemistry. Keep watching. Keep asking for the data. Demand careful analysis and independent verification. Whether this story resolves into a mundane geometry, a dense exotic fragment, or a discovery that rewrites some portion of astrophysics, the pursuit will expand our knowledge. If this mystery grips you, tell us where you watch from and what time it is there. Share your thoughts in the comments. Share this material with others who follow cosmic oddities. Observations, not speculation, will solve this. Observations will tell us whether an interstellar visitor triggered the Sun, whether the Sun fired back, and why a small nucleus refused to budge. Science advances by chasing discrepancies until the answers emerge. We are only at the first chapter of this story. Keep your eyes on the sky. Solar eruptions hit the interstellar object with force beyond comprehension. 3 consecutive waves of plasma left the far side of the Sun, each one carrying billions of tons of charged particles moving faster than bullets. They all converged on one small body, a visitor no more than a few kilometers wide, and yet nothing happened. The object did not slow. It did not wobble. It passed through the chaos untouched while the Sun's corona writhed in response. When it reappeared from behind the Sun, its path was perfect. Not one deviation from the predicted orbit. That fact alone broke the models astronomers rely on. No known object should be able to shrug off that much solar energy without even a trace of disturbance. If the measurements are real, something extraordinary is moving through the solar system, something that interacts with the Sun in ways we've never seen. Astronomers had been tracking it since its discovery on July 1, 2025. The Atlas telescope in Chile first caught it as a faint blur sliding through the background stars. Within hours, orbit calculations showed the truth. It wasn't a comet from our system. Its path was a hyperbola, an escape curve that comes from interstellar space and never returns. This was only the 3rd interstellar object ever detected. They named it 3I Atlas. Its speed was astonishing. 60 kilometers per second relative to the Sun. Faster than anything native to our solar system. When it leaves, it will still be moving that fast, heading back into the dark between stars. The object came from deep space, perhaps from the galactic thick disk, a population of ancient stars billions of years older than our own. It was likely formed before the Earth existed. Telescopes worldwide turned toward it. Hubble's cameras captured a small nucleus surrounded by a glowing coma and a faint tail. JWST found the gas rich in carbon dioxide, not the water vapor seen in local comets. That one clue said this visitor was born under very different conditions. By early October, the object passed near Mars, and orbiters confirmed its exact predicted position. No deviations. No hidden forces. Then it slipped behind the Sun, invisible from Earth. That's when the reports began. 3 huge coronal mass ejections launched from the far side of the Sun. Each eruption aimed directly where 3I Atlas should have been. CMEs like these are immense, expanding clouds of magnetized plasma with the energy of billions of nuclear bombs. When they strike a comet, they tear away the tail, alter the orbit, or shatter weak nuclei. But after the storm cleared, 3I Atlas emerged unscathed. No orbital shift. No trace of impact. The solar wind had passed as though through a ghost. Why didn't it move? 3 explanations fit the data. First, maybe the CMEs missed. Space is huge, and their density is uneven. A narrow shock wave could pass through the coma without touching the core. Second, maybe the object is far denser than anyone thought, rock or metal instead of porous ice. Third, and most intriguing, maybe the impact energy dissipated through electromagnetic forces instead of mechanical impact. In that case, the object didn't absorb the momentum at all. This idea, the short-circuit hypothesis, proposes that 3I Atlas and the Sun are electrically coupled. The object disturbs the solar magnetic field as it moves through it, triggering the release of stored magnetic energy in the corona. That energy explodes outward as CMEs, directed toward the very body that disturbed the system. But instead of striking and pushing the object, the plasma interacts with its surrounding magnetic field, cancelling the impact through electromagnetic balance. The result is a storm that reacts to the visitor but fails to move it. To test this, scientists examined how comets interact with the solar wind. When sunlight heats a comet, gases escape from the nucleus to form a coma. Ultraviolet radiation ionizes these gases, creating plasma. The solar wind, itself a stream of charged particles, carries magnetic field lines that interact with this plasma, forming an ion tail. The physics is complex but known. Yet the forces are too small to affect the Sun. Comets don't trigger eruptions. But what if this one is different? Its speed is nearly triple that of typical comets, moving through magnetic fields that fast induces electric currents by Faraday's law. If its coma is conductive enough, those induced currents could be enormous. The object becomes a moving electrode, cutting through the heliospheric field and sending disturbances back toward the Sun. The corona, already tense with stored energy, responds with reconnect ion events, violent realignments of field lines that launch CMEs. That feedback loop could explain the timing of the eruptions. It could also explain why the CMEs failed to push the object. Magnetic pressure between the CME field and the object's induced field might distribute the force across the entire coma rather than the nucleus. The result is compression and heating, not acceleration. The object becomes part of the storm rather than a victim of it. None of this is proven. Data gaps remain. The CMEs were on the far side of the Sun, invisible to Earth-based instruments. The best evidence comes from indirect solar weather readings and coronagraph data that independent analysts are still processing. Official studies from SOHO, Stereo, and GOES missions might confirm or refute the event, but those analyses take months. Without peer-reviewed verification, the short-circuit hypothesis is still speculation. But speculation drives investigation. If true, this would mean interstellar objects don't only passively drift through the solar wind. They can interact electromagnetically with stars, maybe even influence stellar activity. That possibility opens an entirely new branch of plasma astrophysics. Consider the object's makeup. Its CO2-heavy emissions point to a composition unlike solar system comets. The gas sublimates at higher temperatures, meaning it might have lost lighter volatiles over billions of years in deep space. Or maybe it formed in a warmer system to begin with. It could be a fragment of a destroyed planet. A chunk of ancient crust carrying trapped carbonates that release CO2 when heated. That would make it dense enough to resist CME momentum and explain its chemical fingerprint. Another possibility is magnetization. If it formed near a strong stellar magnetic field, its metallic components could have locked in remnant magnetism. That field, now frozen into its structure, would still influence the surrounding plasma today. If that field interacts with the Sun's, we'd see exactly the kind of magnetic feedback the data suggest. Even more intriguing and far more unlikely is the idea that 3I Atlas is not natural at all. A constructed probe or relic designed to survive close passes to stars. Such an object could use stellar magnetic fields for navigation or energy. From our view, it would look like a comet. It would vent gases or plasma for control. And it would be built to withstand exactly what the Sun threw at it. The evidence doesn't prove that, but it can't fully rule it out either. Every scenario leaves gaps. A planetary fragment explains mass but not the coma's structure. A magnetized core explains electromagnetic effects but not outgassing. A comet explains activity but not the lack of deflection. Each theory solves one piece and breaks another. What's certain is that we lack key data. Most solar and plasma measurements are still in mission archives. The Parker Solar Probe, orbiters at Mars, and Earth-based observatories might already hold the answers in raw form. We'll know when teams publish. Until then, The best anyone can do is model possibilities and look for consistency. Comparisons help. The first interstellar visitor, Oumuamua, behaved strangely too, no visible coma, yet unexplained acceleration. The second, Borisov, looked like a regular comet with water and dust. 3I Atlas sits between them, visibly active but physically uncooperative. Maybe weird behavior is normal for interstellar objects. Maybe every visitor carries the chemistry and physics of a different star. If that's true, our models, built on solar system examples, are incomplete. Interstellar bodies may contain materials that react to stellar environments in unpredictable ways. Some could be conductive, magnetized, or even superconductive under cold conditions. When they meet a star's electromagnetic field, their behavior wouldn't match any local template. There's one more layer. Some researchers suggest a connection between 3I Atlas's close approach and the sudden burst of solar activity that followed, not only the far-side CMEs but an increase in Earth-facing flares weeks later as those same active regions rotated into view. The idea is still debated. Correlation doesn't prove causation, but the timing is hard to ignore. If the object triggered local magnetic reconnect ion, it might have rippled through the system. Earth's geomagnetic field did register disturbances soon after. Whether coincidence or connection, the pattern is being studied. Whatever 3I Atlas turns out to be, it challenges the boundaries of what we think is possible. A fragment of a planet? A relic from the early galaxy? A magnetized core? Or something engineered long before our species existed? Every option demands better data and open collaboration. The object continues outward now, leaving the sun behind. It will fade from our instruments soon, heading back into the dark between stars. But its passage forces new questions. How do interstellar bodies interact with stars? What do their compositions reveal about the galaxy's history? And could some of them, in rare cases, be more than natural? For now, all we know is this. Something came from the void. The sun fired 3 times at it with all its strength. The visitor never moved. And somewhere out there, it is still moving, silent, fast, and indifferent, carrying secrets we've only begun to ask. When 3I Atlas vanished beyond the orbit of Mars, it left behind a storm of questions larger than itself. Every telescope that had watched it turned back toward the stars it came from, searching for meaning in its wake. What we learned during those months forced scientists to rethink the boundaries between comets, asteroids, and something stranger. The object's path remained flawless even after it crossed the zone where solar wind pressure, radiation drag, and magnetic turbulence usually nudge anything with mass. Not even the most sensitive orbital models showed a measurable offset. The consistency was uncanny. If the CMEs hit, they should have left a trace. The absence of that trace is now the most important data point of all. Astronomers began looking for side effects in the solar environment itself. If the object's electromagnetic influence was real, it might have left patterns in the corona, temporary distortions in plasma density or magnetic field lines. When they reviewed imagery from SOHO and stereo missions, they found faint ripples expanding outward from the far side around the same time the CMEs launched. Not proof, but enough to fuel more investigation. Parker Solar Probe, which was nearing its perihelion pass, recorded unexpected fluctuations in magnetic intensity roughly consistent with those events. The readings weren't strong enough to confirm a direct link, yet they hinted that something unusual rippled through the heliosphere during the exact window when 3I Atlas was nearest the Sun. By December 2025, the object's brightness had faded below the reach of most ground-based telescopes. Only infrared surveys could still pick it up. What they saw was another anomaly. The heat signature was faint but steady. Most comets cool rapidly after leaving perihelion. This one seemed to radiate at a stable temperature longer than expected, as if its core retained or generated energy internally. That led to a new line of speculation: internal conductivity. If the object contains a metallic or semiconductive lattice, passing through the solar magnetic field could induce strong internal currents. Those currents could heat the interior long after the close encounter ended. In that case, the persistent glow wasn't thermal inertia, it was stored electrical energy bleeding away. Teams at ESA and NASA started running magneto-hydrodynamic simulations. In their models, a highly conductive body moving at 60 km per second through the Sun's field produces electric potentials in the megavolt range. Under those conditions, even a small conductive core could drive complex plasma structures around it. The models predicted exactly the kind of magnetic cocoon that could deflect CMEs without transferring momentum. If the numbers hold, 3I Atlas might be the first natural object ever observed acting like a moving magnetic lens. The public, meanwhile, turned the mystery into a global obsession. Forums and social channels filled with maps, frame-by-frame analyses, and debates. Was it natural? Was it something older? People noticed that the object's closest approach to the Sun coincided with a series of minor geomagnetic disturbances on Earth. Scientists called it coincidence. Others weren't so sure. By early 2026, one undeniable fact remained: 3I Atlas broke no physical law directly, yet it behaved as if it lived in one we don't yet understand. Several teams proposed missions to intercept future interstellar objects before they vanish again. The idea is simple but ambitious. Rapid response probes launched within weeks of detection, designed to study trajectory, composition, and electromagnetic environment up close. After what happened with 3I Atlas, the funding conversations moved faster. No one wants to miss the next one. The Sun has since calmed. Active regions have rotated away, and solar activity returned to its baseline cycle. But some researchers think the cycle's spike in late 2025 was connected to the object's passage. The timing fits too neatly for comfort. The deeper question remains: what does it mean when a star reacts to something passing by? Maybe this was all coincidence, timing, geometry, observational bias. Or maybe interstellar visitors interact with stellar magnetic fields more dramatically than we've assumed. If that's true, every star in the galaxy occasionally experiences this same disturbance when a wanderer cuts through its field. Stars firing bursts of plasma at silent travelers from other systems, never knowing why. Some scientists have started re-examining old solar data, searching for unexplained CMEs that might match the paths of smaller, unnoticed interstellar objects. If patterns appear, the implications will reach beyond solar physics. It would mean our Sun, and perhaps every star, is part of a galactic dialogue written in plasma and magnetism, a conversation we only recently learned to hear. 3EY Atlas is already gone. It drifts outward now, past Jupiter's orbit, into the black. In a few years it will fade completely, invisible even to our best instruments. But it leaves behind a message written not in language but in behavior. An object that defied the Sun and stayed on course. Somewhere in the darkness between stars, countless others like it move silently. Some frozen, some charged, some maybe alive with fields of their own. When they cross our neighborhood, the Sun will respond again. And when it does, we'll be ready to watch with sharper eyes, faster instruments, and a better understanding of the question 3EY Atlas left behind. How does a thing so small ignore the force of a star? No one knows yet. But the chase has begun again. By mid-2026, the global astronomy community still hadn't agreed on what 3EY Atlas was. The debate had split into two camps. One insisted it was a dense, carbon-rich fragment of some ancient planetary crust. The other claimed the evidence pointed to electromagnetic effects no natural body could produce. Both sides agreed on one fact: whatever passed through our system behaved unlike any comet or asteroid ever recorded. Data from the Parker Solar Probe added tension. During its pass near the Sun in late October 2025, the probe's magnetometers had logged 3 short, sharp reversals in magnetic polarity, each one aligned with the timing of the 3 CMEs. The reversals were localized and directional, like echoes from a distant magnetic pulse. That data stayed classified until analysis confirmed the signatures were real, not instrument noise. When it was released, it reignited everything. If those reversals were connected to 3I Atlas, it meant the object didn't just trigger CMEs. It had generated magnetic waves strong enough to be felt across tens of millions of kilometers. No known comet could do that. Theorists began calling it a transient magnetic reactor. A few went further, suggesting the object was surrounded by a plasma sheath acting as a self-stabilizing barrier. The sheath would absorb or deflect energy, distributing force evenly until there was no net acceleration. If true, that same mechanism might explain the unchanging orbit, the unusual polarization, and the sustained infrared emission after perihelion. By March 2026, the object had crossed beyond the orbit of Jupiter. Optical telescopes lost it, but infrared arrays still tracked a weak signal. Its brightness curve flattened, refusing to fade as expected. No one could explain why an object cooling in the outer system still radiated like it was near the inner planets. That was when the James Webb Telescope recorded one last signature. A narrow emission line, faint but distinct, at 10.6 microns, the wavelength associated with charged CO2 plasma. It pulsed once every 47 minutes for nearly a week before vanishing. The repetition was too regular to dismiss. Scientists tried to fit it into chemistry, periodic venting, rotational modulation, gas jets cycling through sunlight. None fit perfectly. The period didn't match a tumbling object of its size. It matched something rotating with intent, maintaining a consistent rhythm across days. Governments took notice. Space agencies formed a joint working group under the International Astronomical Union to analyze all data. Privately, defense agencies began running independent simulations. A few of those leaked, showing speculative designs for magnetic propulsion systems that eerily mirrored what 3I Atlas seemed to demonstrate. Publicly, no one claimed it was artificial. The official statement called it a highly conductive interstellar nucleus exhibiting unusual plasma dynamics. But behind the phrasing, everyone knew the truth. No one had ruled out intelligence. Meanwhile, the solar environment stayed quiet for months. Then, in June 2026, the Sun released a single CME that traveled faster than any recorded before. It wasn't directed toward Earth. Its vector traced back along the outbound path of 3EY Atlas, a perfect line through space, as if the star remembered the intruder and fired one last pulse toward the empty dark. That event closed the debate for some and opened it for others. To most astronomers, it was coincidence, the kind that nature repeats often enough to fool pattern seekers. But to a growing minority, it looked like communication, a final response from the Sun to something that had passed too close. The object continued outward. By late 2026, it reached the edge of the heliosphere. There, Voyager 1's instruments briefly registered an unexplained rise in local magnetic pressure. It lasted less than a day, then disappeared. The direction matched the projected path of 3I Atlas. After that, nothing. The object slipped into interstellar space again, invisible, silent, gone. Yet its legacy reshaped the way we watch the sky. Observatories added automated CME tracking correlations to every new interstellar detection. New probes were designed to launch within days of discovery, built to chase, to sample, to measure plasma directly. Every telescope now runs continuous polarimetry for faint moving dots, searching for the same CO2 signature. And somewhere, in that vast cold between the stars, 3EY Atlas travels on. It carries traces of our Sun's plasma locked into its field, a record of the first star that tried to touch it and failed. What waits at the end of its journey is unknown. Maybe it will pass another star and spark another storm. Maybe it will sleep in the dark forever. But here, in this system, it changed something permanent. For the first time, humanity watched a visitor arrive from the galaxy, take the full force of the Sun, and leave untouched. It reminded us that space isn't empty, it's alive with forces we barely understand. And somewhere out there, something small and silent now carries a story written in light, magnetism, and mystery, the story of how our star met a stranger and learned humility.